Section 3.7, Optimization Problems. When we talk about optimization in calculus, we are talking about maximizing the volume, minimizing the cost, minimizing the amount of materials used, etc. Maximizing the mileage, things of that nature. So let us imagine a sheet of paper that's 9 inches by 12 inches, and we want to make a box out of it with an open top. Here are several ways that that box could turn out, depending on how we cut the sheet of paper. And as you can see, they all have different volumes. And short of actually cutting a bunch of boxes to find the different volume that we might have, perhaps we could use some calculus to actually find what dimensions would give us the greatest volume. So if we were in class right now, we would be creating these little boxes. We'd be cutting them, and I would have each little group cut off a certain amount on their piece of paper to fold up the edges. And you can see that we would actually have to cut the same amount off of each corner so that when we folded those edges up, they would meet. Right? So we don't know what we're going to cut off, but let's say it's X in this direction and X in this direction. Well, that would make the width of the paper 9 minus 2X, and that would also make the length of the paper 12 minus 2X. And if we were in class, each one of you would have a different color of paper, such as these listed here, and I would tell you what your X needed to be, and everybody would make their box, and from there we would look at the boxes and try to guess which one held the most volume. And then we would do the calculus. So we know for volume of the box, it's length times width times height when we're looking at this kind of box, but sometimes we have other solids, so a better formula would be area of the base times the height. Well, in this case, the area of our base would be this dimension times this dimension, and then our height is X. Now, this is our volume, and our volume is a function of a single variable, X. And we can FOIL this part out, getting 108 minus 42X plus 4X squared, and then distribute the X across. And there's our volume as a function of X. Now we know that what we need to do is take the derivative of that and set it equal to 0. But there's something we really should think about before we continue on, and that is, what would be an acceptable domain? What is the largest we could cut our corner? What is the largest piece? Well, the biggest we could cut would be less than 4.5 inches, because if we cut 4.5 inches, then this piece of paper is now cut into half. So our domain is from 0 to 4.5. So we now are going to be looking for the derivative set equal to 0 to find our maximum, and we want our answer to be between 0 and 4.5 inches. So we know how to do the calculus, taking our volume, find the derivative of it. We can factor out a 12 to make this a little bit easier. And we can see that when we go to try to solve this isn't factorable nicely, so we're going to have to use quadratic formula. And when we do, we get 7 plus or minus the square root of 13 all over 2. Now, I don't know what the square root of 13 is, but I do know the square root of 9 is 3, and the square root of 16 is 4, so clearly this has to be some number between 3 and 4. So we are going to take 7 and add and subtract some number between 3 and 4, maybe 3.5, I don't know, and then divide by 2. Well, the calculator tells us that we have two answers, 1.697 or 5.302, which we have to exclude this because our domain is from 0 to 4.5 inches. So what this tells us is the most we should cut off for the greatest volume is about 1.697 inches. Now, how do we know that we have gotten a maximum at this value, a maximum volume at this value for X? Well, we can take the second derivative. Here is my first derivative, and taking the second derivative gives us this. And when we evaluate the second derivative at this X that we're going to use, we get a negative answer. And that tells us that we are concave down, which means I have a maximum at 1.697. And then, of course, the question we want to know is, what is that volume? Well, that volume, we would substitute this into our volume formula and get this answer. Now, were we in class, we would have experimented and everybody would have made their boxes, and we would have found that somewhere between 1 and 2 inches is going to be where our maximum volume occurs. And you can see that 1.697 is here between 1.5 and 2, so somewhere in here is our greatest volume. That is what this section is all about. So our key in working these problems is going to be to identify our primary equation, the one we want to take the derivative of, and our secondary equation that we're going to use to substitute into the first so that we get an equation in one variable. Example 1. Find the dimensions of a rectangle with perimeter 100 feet whose area is as large as possible. So we want to maximize the area. That makes our area formula our primary equation we're going to work with. And we know if we draw a box, we have x times y. There's our area. Now the perimeter is 100 feet, so the variables x and y are related by the equation 2x plus 2y is 100. We can divide everything by 2, and we can also recognize that we're going to use this equation to substitute into this equation to get an area in the form of one variable. So why don't we take this and solve it for y? Y equals 50 minus x. Substitute 50 minus x right there. And we now have our area formula. And now we are ready to take the derivative. However, let's determine what our constraints are for x. Area is going to be 0 when x is 0 and when x is 50. So our domain has to be between 0 and 50. Okay. Now we're going to take the derivative. Of course, the derivative of 50 minus x squared is 50 minus 2x. The derivative equals 0 when x is 25. That is our critical number. But we are checking absolute maximum. So what do we do when we look for maximum? Not only do we check at the critical numbers, but we check at the endpoints. So there's a couple of ways we can do this. One is to take the second derivative, and since my second derivative is negative, my area function is concave down, so we have our maximum at x equals 25. But another way to do it is to substitute these values into your area formula and confirm that at 25 we have our maximum area. 5-step procedure for finding maximum and minimum optimization problems. 1, draw the appropriate figure and label the quantities relevant to the problem. 2, find a formula for the quantity to be maximized or minimized, and we're going to take the derivative of that eventually. 3, use conditions stated in the problem to eliminate variables expressing the quantity as a function of one variable. So you're going to use that secondary equation to do that. 4, find the interval of possible values for this variable. That's your domain you're looking at. And then 5, if applicable, use techniques of the preceding section to obtain maximums and minimums. Here is the box example we just did. An open box to be made from a 16 by 30 inch piece of cardboard by cutting squares of equal size from the 4 corners and bending up the sides like this. So again, we have that this is 30. We're going to take off x and x. So this becomes 30 minus 2x. When folded, this becomes 16 minus 2x, and my height is x. So here's our volume formula in the dimensions. Here we can distribute. We know that since my shorter side is 16 inches long, that I have to cut actually less than 8 to still be able to have a box. And now we're going to take the derivative, which is here. Setting it equal to 0 and solving it gives me 2 possible places. So here are my critical points. 12 is outside of the interval from 0 to 8, so we can exclude that one. So now we're checking our endpoints at 0 and 8 and at 10/3. And it turns out that 10/3, of course, is going to give us our maximum volume. Okay, here's a problem for you engineers out there. Figure 6.25 shows an offshore oil well located at a point W that is 5 kilometers from the closest point A on a straight shoreline. Oil is to be piped from W to a shore point B that is 8 kilometers from A by piping it in a straight line underwater from W to some shore point P that's between A and B, and then on to B via pipe along the shoreline. Now, the cost of laying pipe is $1 million per kilometer underwater and $500,000 per kilometer over land. Where should the point P be located to minimize the cost of laying the pipe? So P is somewhere here. Now you might be saying, well, why don't we just go straight to A, that's the shortest distance, and then from A to B, that distance. Well, maybe that's not the minimum cost. So we're going to let X be the distance in kilometers between A and P. So that would make the distance from P to B 8 minus X. And from figure 6.2.5, the length of the pipe underwater is the distance between W and P. And so we have, by Pythagorean theorem, x squared plus 5 squared is WP squared. So we can get this length to be the square root of x squared plus 25. Now also, the length of pipe over land is the distance between P and B, which is this 8 minus x. So the total cost in millions. Now let us remember, 1 million underwater. This is my distance underwater. The coefficient would be 1, so that I can use 1/2 for the cost on land, which is $500,000 per kilometer or $500,000. Much easier to use 1 there and 1/2 here than it is to use 1 million here and 500,000 here. Okay, so our cost is going to be the square root of x squared plus 25 plus 1/2 of 8 minus x. Now, the distance between A and B is 8 kilometers. So the distance between A and P has to satisfy the x between 0 and 8. So that's an important thing to know. So here we go. We're going to take the derivative of this. All right, so the derivative of our cost, that is x squared plus 25 to the 1/2, which is going to give us 1/2 x squared plus 25 to the negative 1/2 times the derivative of x squared plus 25, so our chain rule. So you can see that the 2's will cancel, and that sends this square root down to the denominator, and then minus 1/2. Now that is our derivative of our cost. And solving this, setting equal to 0, we get this, and we get, with a lot of algebra, we get eventually that x is plus or minus 5 over the square root of 3. And here's our algebra. Now, obviously, we cannot have negative 5 over the square root of 3 because we cannot have a negative length. So we have to throw that out. So 5 over the square root of 3 is our only critical point. Now this point lies in the interval from 0 to 8, so the minimum cost has to either occur at the endpoints or at this critical number. Once again, you could make a table. Here is our x values, and here is our cost. Or you could take the second derivative, which is a little bit cumbersome because we have to use quotient rule. And it turns out that our second derivative evaluated at 5 over the square root of 3 is positive, which means we are at a minimum because we're concave up. And you can see that the numbers confirm it. So these can get difficult because of all the hidden algebra involved, but the idea is the same. We are going to find a function of one variable and take the derivative of it, set it equal to 0, use the solutions that work with the constraints of the problem. Here's another nice example to look at. Find the radius and height of the right circular cylinder of largest volume that can be inscribed inside of a right circular cone. And this cone has a radius of 6 inches and a height of 10 inches. Okay, we want the cylinder of largest volume. So what we're going to have to take the derivative of is a cylinder. So our cylinder formula is pi r squared h. But you'll notice hiding in this picture is similar triangles. So r to h equals 6 to 10, or you can think about if this whole thing is 10, I can call this h and this 10 minus h. So we have this relationship. 10 minus h to r equals 10 to 6. And in that case, again, since we're going to take the volume here, we want to maximize the volume. It'd be nice to get it in terms of one variable. So if we solve this for h, we can make that substitution for h. So making that substitution for h gives us this volume. Again, our radius must be between 0 and 6. Since the radius of the cone is 6, I have to stay in that constraint. And we're going to take the derivative of our volume formula, which is here. Derivative is 0 at 4, and then if we check the endpoints. And you can once again see that we can find the volume at 0 and 6 and 4, and clearly that's our maximum volume. We can also take the second derivative and evaluate it at 4. And my second derivative is going to be negative at 4, meaning we're at a maximum. I leave example 5 for you and 6. These are interesting examples for you to read and work through. And your TPs for this section, numbers 9 and 11.